In this video, we're going to look at a way of taking a linearly independent sequence in a finite dimensional vector space and extending that, so adding some more vectors to make it into a basis. Once we've done that, we'll be able to prove that every finite dimensional vector space actually has a basis. So here's the key lemma called the extension lemma. What it says is that if you've got a linearly independent sequence, so I've written this as curly L, and the terms in the sequence are L1, L2 up to Ln. And if you've got a vector v which does not belong to the span of L, then the sequence that you get by adding v to the end of L is linearly independent. So here, L comma v there, all that means is the sequence you get by taking L1 and then L2 and then so on up to Ln and then adding v on the end. Here's how the proof works. Let's suppose that on the to the contrary, LV is linearly dependent. So that means there exist scalars a and a1 up to an such that not all of those scalars are zero and the linear dependence relation here holds. Now it can't be that the scalar a was zero. If the scalar a was zero, then you could get rid of this bit from the linear dependence, and what you would have is a linear dependence on L1 up to Ln. Such a thing can't be because L1 up to Ln are assumed to be linearly independent. So it must be that actually the scalar a was non-zero. But if the scalar a is non-zero, then you can rearrange this. So we will subtract the sum over from both sides, moving it onto the right-hand side of the equation, and then multiply through by the inverse of the scalar a, which exists because we've just established that the scalar a was not zero. When we do that rearrangement, what we get is this expression at the bottom here. But that expression tells you precisely that v is an element of the span of L. So that gives us our contradiction because we were assuming v was not an element of the span of L, and therefore L followed by v must be linearly independent. So in short, what this lets you do is to take any linearly independent sequence, and then if you've got a vector which is not in the span of that linearly independent sequence, you can add it onto the end of that linearly independent sequence and you get another larger linearly independent sequence. And that's the key to our result about extending linearly independent sequences to bases. So here's the result that allows us to do this. The theorem says if you have a finite dimensional vector space V, remember that means that there is a finite spanning set sequence inside V, and if you have a sequence L, which I've written as L1 up to Lk, which is linearly independent, then there is a basis of V containing L. And the way the proof works is to take this finite spanning sequence for V, which we know exists, and add on some of the terms from that spanning sequence to L, and to show that when we do this in a particular way, what we end up with is a basis for V which contains L. So let's do the proof. As I said, we begin by noting that there is a finite spanning sequence v1 up to vm of v because that's the definition of being a finite dimensional vector space. We're now going to define a sequence of sequences of elements of v as follows. We let the first thing, or the zeroth thing in this sequence, just be this linearly independent sequence L. So L0 is just L. Then we define the sequence recursively as follows. So Li plus 1 is equal to one of two things, or two cases in the definition. If Vi plus 1 is in the span of Li, then we just let Li plus 1 be Li again. On the other hand, if Vi plus 1 is not in the span of Li, then we let Li plus 1 be the sequence you get by taking Li and adding Vi plus 1 on the end. So L0 would be L, and L1 would be either L again, or L followed by V1, and so on. So we're going to show that each of these sequences L0, L1, L2, and so on are linearly independent. The zeroth sequence, L0, is L, and L was assumed to be linearly independent. So for sure, L0 is linearly independent. The proof then continues by induction because we've now just done the base case. But the inductive proof is really simple because there are just two possibilities for Li plus 1. So inductively, we assume that Li is linearly independent, and then Li plus 1 is either equal to Li, in which case it's certainly linearly independent because by the inductive hypothesis Li was linearly independent, or it's Li followed by something which is not in the span of Li, and the extension lemma tells you that such a thing is linearly independent. So that makes the induction proof go through, and that means that all of the terms in this sequence, L0, L1, L2, and so on, up to Lm, are all linearly independent sequences. What we're going to argue is that actually the last term in that sequence, curly L subscript m, is a basis for V. So to do this, what we will do is show that for all I less than or equal to m, we have that each of the things v1 up to vi is in the span of Li. And again, we'll do this by induction. And again, it's clear for I equals 0. For I equals 0, there's nothing to say. So it's not claiming anything at all. So it's definitely true. For the inductive step, let's suppose that v1 up to vi are all elements of Li. Now, Li is contained in Li plus 1. So that means v1 up to vi are also in the span of Li plus 1. But also, if you look at the two cases in the definition of Li plus 1, in both of those cases, its span is guaranteed to contain Vi plus 1. So the span of Li plus 1 contains v1 up to vi, and it contains Vi plus 1, and that makes the induction go through. Let's now consider the final term in our sequence of sequences. That is Lm. It's linearly independent because we know that all of the Li's are linearly independent. So all of the curly L subscript i's are linearly independent. And its span, as we've just seen, contains the whole of the spanning sequence v1 up to vm. If it contains all of that spanning sequence, then actually, because subspaces are closed undertaking linear combinations, it contains any linear combination of v1 up to vm. But every vector in V is a linear combination of v1 up to vm. So the span of Lm contains every vector in V, and that means the span of Lm is all of V. We've now shown Lm is linearly independent. We know that it is a spanning sequence, and therefore Lm is a basis of V which contains L. So let's look at how that proof works in a concrete example, because I want to show you that actually this is not just a proof method, but something which can actually be used in practice. So if you had a linearly independent sequence inside a finite-dimensional vector space, you could use the technique of that proof in practice to work out what's going on there. So let's do this example. We're going to start off with a linearly independent sequence, curly L, consisting of one vector, just L1, which is the vector 1, 2, 3, sitting inside R cubed. We know a spanning sequence for R cubed. We know that the standard basis E1, E2, E3 is a spanning sequence for R cubed. So here, as usual, when I write E1, E2, E3, I mean the standard basis. So E1 is 1, 0, 0, and E2 is 0, 1, 0, and E3 is 0, 0, 1. So we're going to use the technique of the proof to produce a basis for R cubed containing L1. So what we do is we create this sequence of sequences of elements of R cubed. The initial one, L0, is just the original sequence, which in our case is just the vector L1. When we work out L1, remember that definition comes in two cases. So we have to determine, is E1 in the span of L0? The span of L0 is just the span of this one vector L1. So it's all the scalar multiples of L1. And E1, 100, is definitely not a scalar multiple of L1. So E1's not in L0, which means we're in the second case of our definition. L1 is equal to the vector L1 followed by E1. So now we need to work out what curly L subscript 2 is. So we have to decide, is E2 in the span of L1? Well, let's work it out. If we want to know if E2 is in the span of L1, well, that's true if and only if E2 is a linear combination of L1 and E1. So we're looking for numbers A and B such that A times L1 plus B times E1 is equal to E2. We want to know if that's possible. So that vector equation is A 2A 3A plus B 0 0 is equal to Z 0 1 0. But this is obviously impossible, because if you look at the second coordinates, that's telling you that 2A must be equal to 1, so A is a half. But if you look at the third coordinate, it says 3A equals 0, so A equals 0, and A can't be 0 and a half at the same time. So this equation is impossible. That means E2 is not in the span of L1, and that means L2 is vector L1, then vector E1, then vector E2. Finally, with a similar method, you can check that E3 is not in the span of L2. So that means L3 is just the same as L2 again. I think there's a little bit of a typesetting error there. That should, of course, be E2 and E1 and E2. That thing then is guaranteed by our proof to be a basis of R cubed, which contains the original sequence, which was just the sequence of length 1 with L1 in it. Okay, so I hope this demonstrates that this method, which we used in the proof, is actually a practical procedure which you could do if you were asked to extend a linearly independent sequence to a basis. We're now able to use our results to prove some of the things which I said were which we needed when we discussed the definition of dimension. So one of the first things which we really needed to know and which we did not know was that every finite dimensional vector space should have a basis. We're now able to prove that. So here it is as a corollary. Let V be a finite dimensional vector space, then V must have a basis. And the proof is now very easy. You just take any linearly independent sequence of elements of V. For example, you could just pick a single non-zero vector in V, and that would form a linearly independent sequence of length 1, as we saw in our previous example. And then you can use the result on the, well, actually not the previous slide, the slide before the previous slide, to extend it to a basis of V. Remember what that result said was that if you've got any linearly independent sequence, you can extend it to a basis. So in particular, every finite dimensional vector space has a basis. So that's good. It means that every finite dimensional vector space has a dimension, because the dimension is the size of a basis. Now that we know that a basis exists always, we can define the dimension, and we know a dimension exists for every finite dimensional vector space. Even better than this, we can also rectify this other problem, which was that it wasn't completely obvious from the definition that a subspace of a finite dimensional vector space was again finite dimensional. So we're able to prove that now. If V is a finite dimensional vector space and U is a subspace of V, we can now prove that U must also be finite dimensional. So let's do the proof. Suppose that for a contradiction that U is not finite dimensional, which means that no finite sequence of vectors spans U. We're going to prove by induction on n that U contains a linearly independent sequence of any size n. So for n equals 1, this is very clear. You just pick any non-zero vector in U, and that is a linearly independent sequence of length 1. Now we'll do the inductive step. So let's think what the inductive hypothesis tells us. It's telling us that there is a linearly independent sequence of length n. We have to now prove that there is a linearly independent sequence of length n plus 1. So let's introduce some notation for a linearly independent sequence of size n. We'll call it Ln. Now that's a finite sequence of vectors, so by our assumption it does not span U. So there must be some vector in U which is not in the span of Ln. So let's call that un plus 1. There is at least one vector not in that span. But by the extension lemma, if un plus 1 is not in the span of Ln, then Ln followed by un plus 1 is linearly independent. So that makes our induction go through. That means U contains linearly independent sequences of any finite length you like. But the problem is these sequences also belong to V. They're elements of U, which is a subset of V. So those linearly independent sequences are also linearly independent sequences in V. But if we just look at the sequence, which has got length 1 bigger than the dimension of V, that is a linearly independent sequence of elements of V, which is bigger than a basis of V. So it's bigger than a spanning sequence in V. But that contradicts the Steinitz exchange lemma, which said that spanning sequences are always at least as big as linearly independent sequences. So we've got our contradiction, and in fact U must be finite dimensional. Okay, we're done. We've rectified some of the problems with our definition of dimension.